Look at a large cargo ship and you'll notice something that seems counterintuitive. The ship is enormous. It weighs over 200,000 tons. The hull is over 400 meters long. The engine is powerful, producing 50,000 horsepower or more. But the propeller, the device that propels this massive ship, seems impossibly small. The propeller might be only 10 meters in diameter. It has just 3 or 4 blades. The propeller blade area is tiny compared to the ship's total size. How can such a small propeller move such an enormous ship? The answer involves understanding propeller efficiency, the relationship between propeller speed and power, and the physics of water movement. The counterintuitive answer is that a small propeller moving slowly is far more efficient than a large propeller moving quickly. A slow-moving propeller in a large diameter creates more thrust with less power than a small propeller moving quickly. Understanding why massive ships have tiny propellers reveals principles of fluid mechanics, efficiency optimization, and the fundamental physics of propulsion. Today we're exploring why ship propellers are so small relative to ship size. The fundamental principle behind propeller design is that thrust comes from accelerating water backward. The propeller grabs water and accelerates it backward. The reaction to this acceleration, according to Newton's third law, is a forward force that propels the ship. The thrust generated depends on 2 factors. The first factor is the mass of water accelerated backward. The second factor is the acceleration, the change in velocity of that water. The total thrust equals mass times acceleration. To generate a given amount of thrust, you can accelerate a large mass of water slowly or accelerate a small mass of water very quickly. A large propeller that rotates slowly accelerates a large mass of water. A small propeller that rotates quickly accelerates a small mass of water. If both propellers generate the same thrust, they perform the same job. But the efficiency is different. The efficiency of a propeller is related to the velocity of the water relative to the propeller. If the propeller accelerates water from 0 velocity to high velocity, energy is wasted. If the propeller accelerates water from near 0 velocity to slightly higher velocity, less energy is wasted. A large propeller moving slowly makes smaller velocity changes to the water. A small propeller moving quickly makes larger velocity changes. The relationship between propeller power and ship speed reveals the efficiency advantage. Power is the rate at which energy is used. A propeller requires more power to move faster. The relationship between power and velocity is not linear. Power is proportional to velocity cubed. If you double the ship's speed, power increases by a factor of 8. If you increase ship speed by 20%, power increases by about 73%. This relationship means that small speed increases require large power increases. For cargo ships, which are not in a hurry, operating at relatively low speeds is far more efficient than higher speeds. Modern cargo ships operate at relatively low speeds, typically 12 to 20 knots. The slow speed is not a limitation. It's a choice based on efficiency. The ship owner could build a faster ship with a larger propeller and larger engine. But the fuel consumption would increase dramatically. The faster ship might consume twice the fuel per mile. The additional fuel cost would exceed the benefit of the slightly faster transit. For cargo that is not time-sensitive, slow speed is optimal. The ship completes its voyage more slowly, but the cost per unit of cargo is lower. The slow-speed diesel engine is the standard marine power plant for cargo ships. These engines typically rotate at 100 to 120 revolutions per minute. This is extraordinarily slow. A car engine rotates at 1,000 to 6,000 revolutions per minute. The slow rotation speed is matched to the propeller speed. The propeller is directly connected to the engine through a reduction gearbox. The reduction gearbox has a ratio of maybe 4 to 1 or 5 to 1. The engine rotates at 100 rpm, and the propeller rotates at 20 to 25 rpm. This slow rotation speed is optimal for efficiency. The propeller blade shape is critical to efficiency. The blade is an airfoil shape, similar to an airplane wing. The shape creates differences in pressure on the two sides of the blade. The pressure difference creates a force that accelerates water backward. The blade angle relative to the water flow must be optimized. If the blade angle is too steep, the pressure difference increases, but the blade also creates cavitation. If the blade angle is too shallow, the blade doesn't create enough pressure difference. Cavitation is a phenomenon that limits propeller efficiency. When the pressure on the blade surface drops below the water vapor pressure, bubbles form. These bubbles are vapor-filled cavities in the water. When the propeller blade moves, these cavities collapse. The collapse creates shock waves and erosion of the blade surface. Cavitation reduces propeller efficiency and can damage the propeller. The cavitation limit constrains how much thrust a propeller can create. A propeller operating at the cavitation limit cannot create additional thrust without cavitating more severely and damaging itself. The relationship between propeller diameter and efficiency is important. A larger diameter propeller can move more water. Moving more water at lower velocity is more efficient than moving less water at higher velocity. This is why large cargo ships have relatively large diameter propellers. The diameter might be 10 to 12 meters. A small, faster ship might have a smaller diameter propeller, maybe 3 to 4 meters. The difference in diameter reflects the difference in speed. The large, slow propeller is more efficient. The number of propeller blades affects efficiency and vibration. A propeller might have 3 or 4 blades. Fewer blades mean lighter weight and less vibration, but more stress on each blade. More blades mean the load is distributed, but the weight and vibration increase. Ship owners optimize the number of blades based on ship characteristics. Slower ships typically have 3 blades. Faster ships might have 4 or 5 blades. The choice involves balancing efficiency, vibration, and structural considerations. The propeller-slip ratio is a measure of how efficiently the propeller operates. Slip is the difference between the theoretical distance the propeller should move the ship and the actual distance traveled. Perfect efficiency would mean no slip. In reality, slip might be 10 to 20%. This means the propeller might make the water move backward at 1 meter per second, but the ship only moves forward at 0.9 meters per second. The lost efficiency is the slip. Optimized propellers minimize slip. The interaction between the propeller and the ship's hull is complex. The hull creates a wake, a region of disturbed water behind the ship. The propeller operates in this wake. The wake reduces the water velocity relative to the propeller. The propeller must work harder to create thrust. The hull form is optimized to minimize wake in the area where the propeller operates. Ship designers model the propeller and hull together to optimize their interaction. Variable pitch propellers provide operational flexibility. A variable pitch propeller can change the blade angle without physically changing the blade. The blade angle can be changed to optimize efficiency for different ship speeds. The variable pitch propeller can also reverse thrust quickly, which is valuable for emergency stops and maneuvering. However, variable pitch propellers are complex and expensive. Fixed pitch propellers are more common on cargo ships where the operational speed is relatively constant. The relationship between propeller size and ship power explains why cargo ships don't use larger propellers. A larger propeller would move more water. But the engine would need to rotate the propeller faster to move the water. The gearbox ratio would need to be different. The power requirement would increase because the engine speed would be higher. The overall system would be less efficient. The current design of small, slow-rotating propellers is optimal. Azimuth thrusters are an alternative to fixed propellers. These thrusters can rotate 360 degrees, allowing the ship to move in any direction. Azimuth thrusters are common on specialized vessels like tugboats and icebreakers. The thruster provides directional control and can generate thrust in any direction. However, azimuth thrusters are less efficient than fixed propellers for continuous operation. Cargo ships prioritize efficiency, so they use fixed propellers despite the directional control limitations. Pod drives are another alternative propulsion system. A pod drive is a propeller mounted in a streamlined pod that extends below the hull. The pod can be rotated to change direction. The pod design is more hydrodynamically efficient than traditional propeller shafts. Some newer container ships use pod drives. The efficiency advantage and directional control benefits appeal to modern ship owners. The propeller hub and shaft assembly must withstand enormous stresses. The shaft rotates slowly but carries enormous torque. The torque at the shaft might be millions of Newton meters. The shaft must be made of high-strength steel. The hub that connects the blade root to the shaft must distribute the torque across the blade root without creating stress concentrations. The design requires sophisticated engineering. The interaction between propeller speed and propeller noise affects ship design. A slowly rotating large propeller creates less noise than a rapidly rotating small propeller. Slower propellers are quieter. This is why cargo ships are relatively quiet compared to faster ships. The quiet operation is a byproduct of efficiency optimization. Quieter operation is beneficial for crew comfort and for marine life, as loud propeller noise can disturb whales and other marine animals. Modern propeller design uses computational fluid dynamics to optimize blade shape. Computer simulations can model water flow around different blade geometries. The simulation calculates efficiency for each geometry. The designer selects the geometry that provides optimal efficiency for the ship's operating conditions. This optimization has resulted in propellers that are more efficient than traditional designs. The reason cargo ships have tiny propellers relative to their size is fundamentally about efficiency. A small, slowly rotating propeller moving a large mass of water slowly is far more efficient than alternatives. The choice reflects the economic optimization of shipping operations. Cargo ships prioritize cost efficiency. The small propeller enables this efficiency. Understanding why ship propellers are small reveals principles of thermodynamic efficiency and optimization under economic constraints. If you're fascinated by how counterintuitive design choices result from deep understanding of physics and optimization, subscribe to the channel. We regularly explore how engineering reveals physics principles that aren't obvious. Understanding propeller design reveals how engineers optimize complex systems for efficiency. Your subscription supports the creation of content that explores how physics principles guide engineering decisions. Thank you for watching and for your interest in understanding how ships achieve efficient propulsion through careful design optimization.